The next topic is acid-base disorders. So just a quick housekeeping thing. There's a difference between when you say acidemia and acidosis. So acidemia or alkalemia refers to the pH of the blood. For example, a pH of 7.25 is acidemia, and the process by which this occurs is osis. So acidosis and alkalosis refers to the process leading to the emia, i.e. metabolic acidosis or alkalosis, or respiratory acidosis or alkalosis. So before we get into how to really interpret an ABG, just quickly want to take a look at the acid-base buffer. So in our body, we have water plus carbon dioxide in equilibrium with H2CO3, in equilibrium with H plus and HCO3 minus. So basically, this is the bicarbonate buffer system, and this is a homeostatic mechanism that involves balancing carbonic acid, H2CO3, and bicarb and carbon dioxide to maintain a normal pH in the blood. If this system fails to function properly, it can lead to acidemia or alkalemia. So any changes in the CO2 or the carbon dioxide means that this is generally a respiratory process, and any changes in the bicarb lead to a metabolic process. So this is a way to approach ABGs in 5 steps. So we'll go through each one of these steps. The first is to determine if there's an acidemia or alkalemia, if the primary cause is metabolic or respiratory, if there is a compensation, if there are secondary disorders, and then ultimately figuring out what is the underlying cause of the acid-base disorder. So step 1. This is very simple. Is it acidemia or alkalemia? So normal pH in the blood is from 7.35 to 7.45. So anything less than 7.35 is acidemia, and greater than 7.45 is alkalemia. So step 2 is to determine the primary disorder, and we will go through all of these in relation to how they affect the acid-base buffer. So for metabolic acidosis, pH is less than 7.35, and because it's metabolic, it's due to an insult on the kidneys, leading to a change in the HCO3 or the bicarb. Therefore, the bicarb goes down, your equation gets pushed to the right, and therefore your H plus will go up. So a decrease in bicarb will lead to metabolic acidosis. In metabolic alkalosis, pH is greater than 7.45, and again, metabolic, therefore a change in the bicarb. So if your bicarb goes up, your equation gets pushed to the left, and thus your H plus goes down. So an increase in the bicarb will lead to a metabolic alkalosis. For respiratory acidosis, pH is also less than 7.35, and because it's respiratory, it's due to a change in the carbon dioxide. If your carbon dioxide goes up, your equation is pushed to the right, therefore your H plus also goes up. Therefore, an increase in your carbon dioxide will lead to a respiratory acidosis. And conversely, for a respiratory alkalosis, the carbon dioxide goes down, the equation gets pushed to the left, and therefore your H plus also goes down, and so a decrease in the carbon dioxide will lead to respiratory alkalosis. So in summary, if your pH is less than 7.35, you have acidemia, and if it's due to a change in the bicarb, so a decrease in bicarb, it's metabolic. If it's an increase in CO2, it's respiratory. And conversely, if your pH is greater than 7.45, if you see that the bicarb is high, it's metabolic, and if you see that the CO2 is low, it's respiratory. And another way to look at it is if the arrows are in the same direction, it's metabolic, and if they're in opposite directions, it's respiratory. Meaning, if your pH is down and bicarb is down, it's metabolic acidosis. pH down and carbon dioxide up, it's respiratory acidosis. pH up and bicarb up, it's a metabolic acidosis. And pH up and carbon dioxide down, it's a respiratory alkalosis. So for metabolic acidosis, we want to see if there's an appropriate compensation, which would mean a decrease in the CO2 to push the equation back towards the left. So in metabolic acidosis, your H plus is up, your bicarb is low, and because it's already pushed to the right, because you're trying to push it back to the left, you're going to try to consume some of your CO2 to push it back to the left. So we use Winter's formula to predict it, and this is that your partial pressure of CO2 equals 1.5 times your bicarb plus 8 plus or minus 2. If your CO2 is within what you calculate for Winter's formula, then you have a metabolic acidosis that is appropriately compensated. If your CO2 is greater than predicted, that means that you have a concomitant respiratory acidosis. And if your CO2 is less than predicted, then you have a concomitant respiratory alkalosis. And for metabolic acidosis, your bicarb is high, leading to your H plus being low. So your equation is pushed to the left, and in order to push it back to the right, you're going to try to increase your CO2. So the equation to use is CO2 equals 40 plus 0.7 times the change in your bicarb. Now for respiratory compensation, there's a lot of things to memorize because you can have acute or chronic respiratory acidosis or alkalosis. But thankfully, we have this hand mnemonic. So each number of your finger is going to determine what is the appropriate change. So the fingers are labeled here, including your thumb, 1, 2, 3, 4, 5. 1 and 2 are acute and acute, 4 and 5, chronic, chronic. Acid, base, acid, base. So each number, like I said, of the finger corresponds to what your correction should be. So for example, for acute respiratory acidosis, for every 10 rise in your carbon dioxide, it should lead to 1 rise in your bicarb, which corresponds to the first digit. For chronic respiratory acidosis, for every 10 rise in your carbon dioxide should lead to a 4-point rise corresponding to your fourth digit of bicarb. For acute respiratory alkalosis, for every 10 fall in your carbon dioxide, it should lead to 2-point decrease in your bicarb. And for chronic respiratory alkalosis, for every 10 fall in your carbon dioxide should have a 5-point decrease in your bicarb. So once you determine compensation, you want to see if there are any concomitant disorders. So this is most applicable in an anion gap metabolic acidosis. So once you determine if you have an anion gap, you will use Winter's formula like we talked about. And Winter's formula will help us determine if there are any concomitant respiratory acidosis or alkalosis if your CO2 is not what is predicted. However, how do we determine if there is also a concomitant non-anion gap metabolic acidosis or metabolic alkalosis? The rule of thumb is that if there is a pure anion gap metabolic acidosis, for every increase in anion, you should have the same decrease in bicarb. And we often use this equation here, delta delta, which is the change in anion gap over the change in bicarb. If It equals, if it's between 1 and 2, it's usually a pure anion gap metabolic acidosis. If it's less than 1, there is a concomitant non-anion gap metabolic acidosis. And if it's greater than 2, there's a concomitant metabolic alkalosis. A more practical approach to this, instead of memorizing that equation, is that you can take the change in the anion gap and add it back to the serum bicarb. Because like we talked about, if there is a pure anion gap metabolic acidosis, for every change in the anion gap should be a change in the bicarb. Therefore, if you take the delta anion gap and add it back to the bicarb, and it's a normal value for bicarb, you have accounted for all of the anion gap. Therefore, it's a pure anion gap metabolic acidosis. If you add it back and it's less than 22, that means that there is a decrease in your bicarb, which is not accounted for through the anion gap. Therefore, there is also a non-anion gap metabolic acidosis. And if it's greater than 26, that means there is more bicarb than there should be. Therefore, there is a concomitant metabolic alkalosis. And step 5 is to determine the cause. So for metabolic acidosis, we split it into anion gap and non-anion gap. And anion gap, we traditionally learned mud piles, methanol, uremia, DKA, polyethylene, isoniazid, lactic acidosis, ethanol, and salicylates. And for normal anion gap, we refer to hard S, so hyperalimentation, Addison's, RTAs, diarrhea, acetazolamide, spironolactone, and normal saline. For metabolic alkalosis, it can be due to loss of gastric secretions, potassium wasting diuretics, overuse of antacids like milk alkali syndrome, and genetic diseases. For respiratory acidosis, you look at things that lead to alveolar hypoventilation. So this is a very broad category. It include things that will cause CNS depression, such as drugs, cerebral ischemia, sleep disorders, any neuromuscular disorder, chest wall abnormalities, pleural abnormalities, things that cause airway obstruction, such as COPD and asthma, and other parenchymal diseases such as pulmonary edema, pneumonia, ILD. Respiratory alkalosis is anything that leads to alveolar hyperventilation. So this can include things such as psychogenic hyperventilation, such as when people are anxious, hypoxia, CHF, infections, things that cause increased intracranial pressure, salicylate toxicity, liver disease, and excessive mechanical ventilation.